Hello, everyone. Well, this is the first of probably many of different lessons that we're going to do, and we're starting off nice and easy with a revision of what surds are. Now, I know for some of you the idea of a surd it just fills you with all sorts of anxiety, but the fact of the matter is, a surd is just another word for a square root, and it's just a touch more complicated than that, but really, the difficulty with surds comes in their styles. And so what we've got is we've got some square roots that end up in nice, neat numbers, like square root 4, square root 16. Square root 4 is 2. All right, square root 16 is 4. We know that, okay? We don't need a calculator. We remember those from when we were young. But a heck of a lot more end up in much less pretty numbers. Okay, square root 2 is 1.41422. And you'll notice I put dot, dot, dot because it actually doesn't stop. They go on forever. All right. Square root 6 is 2.4948, blah, blah, blah. And it actually never repeats. And it goes on and on and on and on. Now, 2 is exactly the same in value as 4. 4 is exactly the same in value, as square root 16. 2 is square root 4. Whereas if I summarize this and say, okay, well, square root 2 is just 1.41 and round it off, well then 1.41 is not exactly square root 2. It's an approximation. Okay? And so what we do, and the reason why we need to know how to deal with surds, is in order to maintain the same value. In other words, if I have exactly square root 2 chickens, I have 1.41422. And if I express that as a decimal, I'd be writing forever and ever and ever. It will never end. So it's just much easier for me just to keep it as square root 2. Same with square root 6 is 2.44948, blah, blah, blah. And it goes on forever. I'm not going to write that as a decimal because it's ridiculous. I'll go on forever. I'll get stuck. My computer would crash. So I'm just going to leave it as square root 6. And we call these exact values. Now we care about exact values because, well, it's accurate. And when maths is all about accuracy, if we weren't about accuracy, well then near enough is good enough. But if we want to do something like an engineering application, or for example when you're doing Pythagoras questions, and we want exactly the correct distance, well then for a lot of values, it's more convenient for us to keep them as square roots. But so enters another couple of scary words, and that's rational and irrational numbers. Now, I touched on before, pardon my writing here, if a square root ends up as a terminating, or should I say, in a terminating decimal, in a fraction, or a whole number. In other words, if we get a neat-ish number that ends, the answer can be 2 or 1/2 or 2.371. But so long as it ends, we call this a rational number because we can get our head around it. But what happens when we do square root 2? And it's 1.4142, blah, 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 blah. And it will continue like pi. It will go on forever and ever and ever. It will never stop. It will never repeat. It will go on and on. We can't get our head around that. Okay? It's nuts. We can imagine what a number that never ends, that goes on for infinity. We can imagine that, but we can't really get a proper understanding of it. And so we call these irrational, because they're crazy. And so what we do with our irrational numbers is we express them as surds. We express our irrational numbers as surds because it's so much neater and it's so much easier for us to deal with. So now we ask the question, what is really a rational or irrational number? How can I tell the difference? Well, like I said before, rational numbers end. In other words, they can be a fraction, they can be a decimal, or they can be a whole number, we call an integer. And so 37.5%. That can be expressed as 0.375, and therefore we see that it ends. It's a decimal that ends, and therefore this is definitely rational. Definitely rational, because it ends. Whereas, let's have a look at 10 times pi. Now, what's pi again? Let's just use our calculator. Shift pi equals. We see that that number goes on and on and on. And it actually doesn't end at 4. It goes on forever. There are people in the Guinness Book of World Records who can remember hundreds of thousands of decimal places of pi, or at least can work it out in their head super quickly. And so pi never ends. So if I do 10 times that number, well, it's just 10 lots of an irrational, or a number that never ends, and therefore 10 times pi is absolutely irrational. We don't understand what that means, really. We know it never ends, but try to imagine numbers that never end. When you think of the furthest distance, add a little bit more. There'll hit a point in your brain where you'll just go, and that's why we call it irrational. It's crazy. Now, here we have one that's a little bit more familiar, like square root of 48. Let's whack it into the calculator and see. Square root 48, boom. Now we see here, this is 6.928203. So we've got 10 places here. I suspect, although I can't be certain, unless it terminates there, I suspect that it goes on forever and ever. We see that there's no repetition, and therefore I would say that this is irrational as well, because it is neither. The answer is neither a fraction. We can't press SD and turn it into a fraction. We can't turn it into a decimal, and it's not a whole number. Or should I say we can't turn it into a terminating decimal. Laying you a moment.